Hi everyone, welcome to my presentation. We will be talking about FIRM-AFL. It's a high throughput gray box fuzzer for IoT firmware using augmented process emulation. So this was originally presented as part of the 28th Usenix Symposium. The authors are from Beijing Key Laboratory of IoT Security Technology and University of California, Riverside. The presentation video is good. The research paper is even better. It gets into a lot of the under the hood details. I highly suggest reading it. We're going to start off with a roadmap. We're going to talk about some definitions, some terminology that's important for understanding all of this. We're going to look at an overview of selected fuzzing frameworks. We're going to look at what AFL is. We're going to see the unique challenges of IoT and firmware fuzzing. We're going to look at what FIRM-AFL does to solve those challenges, to address them. And we're going to look at the evaluation of FIRM-AFL and how it actually performs. Background. So there's some important concepts and definitions we need to know. For anyone who's not familiar with fuzzing, this is the automated process of using automated tooling to feed permutations of seed data into a program and observing its behavior at runtime. As technical as it is, it's kind of an unintelligent process. Rather than trying to find vulnerabilities, what it looks for is crashes, or in some cases, undefined behavior like out-of-bounds memory access, and it does so by looking for code coverage. It's not able to intelligently guess where problems are. What it does is it attempts to execute every possible branch of code available, take every possible execution branch and record the behavior. To do so, they generally use what we call instrumentation, which is the systematic injection of profiling logic at critical points in the binary. If we have source code available, this is placed in the compiled binary during compilation time. If we only have binary available, the software is generally emulated, and we do this during execution time. And there's an overhead, there's a cost to that. QEMU we're going to spend some time talking about AFL, which is what FIRM-AFL is based on. QEMU is how AFL emulates the hardware stack. It's different from a hypervisor. Hypervisors like VirtualBox and Hyper-V emulate operating systems. Effectively, they emulate software running on your hardware, whereas QEMU is able to do that, but it's also able to emulate entire hardware stacks altogether, such as MIPS or ARM processor architectures, and get them to run on your desktop x86. We're going to talk about some common fuzzing frameworks right now. So this was taken from the paper. There's two things we should pay attention to. One is Firmidine. This is a firmware emulation platform. It can do fuzzing for known vulnerabilities, but it does not implement any sort of code coverage. It does have high compatibility and hardware support, as it can emulate whatever hardware it needs to run. Actually, I take that back. It can only emulate ARM and MIPS is all it actually supports according to its documentation. And it has medium throughput, and it can't detect 0 days because, once again, it can't do code coverage. It can only fuzz it can only fuzz to create a proof of concept for known vulnerabilities, known behavior that exists. And we have AFL, which is very important to our conversation. It has low compatibility because it's unable to support different types of hardware architectures, but it does have high throughput, and it can detect 0 days. We're going to talk about what AFL is, for anybody who may not know. AFL is a gray box fuzzer. It uses instrumentation to perform guided fuzzing by feeding basically permuted input into a program. This is kind of what it looks like over here. Its goal is to take as many unique paths as it can, and it causes crashes, and that's how it knows it found a vulnerability. So if there is a vulnerability that does not cause a crash, American Fuzzy Lop AFL cannot detect it. So that's a shortcoming of it. Different things like libfuzz may be able to overcome this, but our focus is on AFL itself. So how does AFL really work? I'm going to give you a simple example so we all see what AFL does, how it works in concrete terms. Here's a very simple main function written in C with a potential heap overflow. We allocate 256 bytes of memory for input. We get a line from standard in. We have no guarantee it's over 256 bytes. We don't do anything with it, so this won't cause a crash. So it wouldn't actually be detected by AFL, but it's a very simple main function we can use as a prototype. So on the left, we see here this is compiled with GCC, no optimization, and this is our main function in x86. If we look over here, this is the same code compiled in AFL, but what we have above and below it is quite a bit of profiling logic. It kind of peppers the code with a lot of function calls that examine program state and see what it's doing and how it's doing it. This is how AFL kind of determines the state of the program. And as we can see, this very simple function has a lot of overhead, right? There's roughly 3 times as much code to execute here, potentially quite much more code for it to execute depending on the complexity of this function call right here. So what if we don't have source code? In not many cases do we actually have source code available for us for firmware. It's generally distributed as firmware files, which we'll get to in a little bit. So if we don't have source code, we can use QEMU with AFL to emulate the execution of the program. Instrumentation is inserted at runtime while it's being emulated. The way this looks is it will fork the binary at critical sections of code and provide an IPC channel back to the server process to understand what's happening in the child. This process is about 2 to 5 times slower than natively running instrumented fuzzing, and with that I mean instrumenting during compilation time. IoT fuzzing has some unique challenges though. If we can use black box style QEMU and binary only fuzzing, why do we need FIRM-AFL? There's several reasons. First of all, firmware is not just a single binary. It's a collection of many data structures. You can't just pop it into AFL and fuzz it because AFL is made to fuzz one executable. We can see in this binary file, this firmware file, this is from an Archer A7, by the way. It was their most recent firmware release online. We have the bootloader, we have some executable image, we have some executable image, we have the file system, and we have some other stuff, compressed data. So it's not something you can just pop right into AFL. The other issue we need to overcome is the architecture. Most embedded devices do not run on the same architecture as your desktop PC. We have MIPS that this one is using, the Archer A7. I have an x86 desktop. I've never seen a MIPS desktop ever in my whole life. So we can't fuzz even the specific binaries in this firmware file using AFL unless if we have a MIPS device. So we could, potentially use AFL on the firmware device or on the embedded device itself and perform the fuzzing natively on the device, but that's really slow. They don't have a lot of processing power. We have hardware dependencies for many of the firmware files that we must overcome. Do we have the same network card as the firmware file expects? Probably not. Do we have the laser rangefinder for our robot vacuum hooked up to our PC? Probably not. So we have to perform some sort of full system emulation. Traditionally with AFL, we would use QEMU for that. We can see there is significant overhead when doing so. The overall execution time increases by nearly tenfold. And something that we'll see is very important later is syscalls, calls to the kernel that interact with the hardware, are 50 to 100 times slower in execution. This is very significant and is going to cause a lot of slowdowns. So in something as critical or in something as compute intensive as Fuzzing, it's critical we have the proper software to do it that is efficient in doing so. How does FIRM-AFL overcome the issue of high overhead system mode emulation with QEMU? Well, so the developers actually came up with a few novel processes. One is called augmented process emulation. They swap out QEMU for FIRMADYNE. FIRMADYNE is specialized at emulating only Linux-based embedded firmware, and it only supports MIPS and ARM, a few flavors of MIPS and ARM, but still only MIPS and ARM architecture. They also perform selective syscall redirection and optimization. These system calls that are very expensive to emulate from the entire hardware stack, from the top to the bottom of the emulator, they selectively emulate certain ones and then optimize other ones so that this process is as efficient as they can get it. Last thing is snapshots. They utilize a copy on write based snapshot mechanism so that every time the AFL calls fork, it takes a snapshot of the machine state, or every time a page is written to, it takes a snapshot of the machine, and now it can quickly restore these snapshots for quicker execution. The architecture of it is not all different from AFL. In fact, if I were to draw an AFL architecture diagram, this whole diagram would probably look exactly the same. This box is exactly the same as AFL, but in the fork server and the child instance, we are using the augmented process emulation. What does the workflow actually look like? So we run AFL, a bootstrap occurs, which is running the hardware emulator that is FIRMADYNE. The developers of FIRM-AFL make the assumption that when you're fuzzing a embedded device, you care about the network activity rather than what it's doing on its local machine, because you generally don't access a embedded device locally. So they make the assumption that, hey, what we want to fuzz is every time a new binary initially invokes network activity, we're going to fork it. So when that HTTP server starts, we're going to fork there and we're going to start fuzzing the HTTP server. When the DNS server starts, we're going to fork it. We're going to start fuzzing it. The rest of this, very similar to AFL. It's going to, except for the snapshots, but it's going to input seed, monitor the response, create a new snapshot on new branches, and repeat. And it'll keep taking snapshots so that it can restore to earlier states. What is bootstrapping that it does? So it launches FIRMADYNE for the system emulation, and it enables virtual machine introspection so that it can instrument the binaries. What does that mean? It means while it's being emulated, virtual machine introspection is enabled, so it can now put its profiling logic up at a higher level that's executed by the emulator, so that to the firmware device itself, the process is completely transparent. They also create a special RAM file that is used to optimize many of these syscalls, things like reading and writing to the file system. This is optimized by using a RAM file rather than translating these system calls down to the actual hardware level on your computer. They virtualize all of it using a RAM file so that it's now a much more optimized architecture. It's much quicker. What ends up getting fuzzed when you use FIRM-AFL? So like I said, it cares about network activity. In these routers, what ended up being fuzzed were several HTTP servers is what it picked up on and started fuzzing, a common gateway interface binary, a DNS server, and an SSH server. So these are the types of things that FIRM-AFL will automatically detect and begin to fuzz. Let's take a moment to talk about creating snapshots. So the way these are created is as the programs are executed, we have lightweight snapshots that are created. When memory is written to, it copies the memory on the write operation and uses that as a snapshot as well. These are used to quickly restore forked children instances back to their original state to speed in the execution. This is something new that they added that was not supported by AFL beforehand. Overall performance. So this is what it's all about. Like I said, like I've stated before, the fuzzing process is not necessarily intelligent. What matters is, I mean, it's technical, but the fuzzing process itself is just keep trying different input until we reach new branches of code execution, and fuzzing is complete when all branches have been mapped, when there's 100% code coverage. So how does this actually do in user mode calculations? So these are all user mode, meaning there's no system calls. This is just CPU bound operations. Almost no slowdown, 0 to 1% using augmented process emulation. There's very little slowdown compared to using user mode AFL. So there's almost no slowdown doing processor bound operations. When we look at syscalls, which what we saw before had a 50 to 100 times slowdown, they were very slow operations. Most of these can be optimized down from 50 to 100, down to just about 1 to 10 times or 1 to 10% slower. Great optimization, but certain things just simply can't be optimized away. When an embedded firmware device that you're emulating wants to do something TCP related, it still has to access your network card. Like, your real network card can't be emulated, it needs to be used. So we still see quite a large slowdown using this, 159% slowdown for TCP operations for this specific syscall. But the file-based operations are much, much quicker. The overall performance this is actually one of the most interesting diagrams that I saw in the paper. This segment right here from D to C represents the syscall optimizations. And on the y-axis, we see the speed, how many test cases per second we can execute. As I've mentioned with fuzzing, the execution speed, the test cases per second, is one of the most important metrics we care about. We want to be able to check as many branches of code execution as possible. We can see many of these here achieved nearly 50 times greater execution for some of the best ones. With just the syscall itself optimized it maybe 50 times quicker in speed. Maybe some of the more conservative ones were maybe only increased in speed about 20, 50, maybe 50% or so. So just optimizing syscalls was an amazing jump in execution speed. The augmented process execution phase, which is the RAM file, the snapshots, FIRM-AFL, things like that. Once again, we saw about a 10-time speed increase for some of these. Maybe the more conservative ones didn't see much of an increase at all. Some of the more beneficial ones, it made them execute in only 1/10 the time. And then so this was APE, Augmented Process Emulation. And then at the very end here, this is the baseline. This is baseline QEMU with system emulation. So we can see baseline with QEMU very slow. It executed very slowly, maybe 5 or 10 test cases a second, if even that. Whereas with these full emulations, some were getting around 550 executions per second. So in the best case, we saw almost 100 times quicker execution speed. As mentioned earlier, what AFL looks for is crashes. It's not intelligent enough to pick out undefined behavior like libfuzzer or some of the other ones, but it does pick out crashes. What we're looking at here on the y-axis is how many crashes were found, and then what we're looking at on the x-axis is how long it took to find them in seconds. The shaded red area is what AFL performs that natively with QEMU running as its emulator. And the other shaded area is what FIRM-AFL was able to perform during testing. We can see that the speed increase is quite significant, actually. FIRM-AFL in many cases is able to almost immediately find issues. It may be within a few minutes, maybe an hour, it's able to pick up a crash extremely quick, whereas when we look at its counterpart with QEMU, I'm not sure what 40,000 seconds is, but it's quite a long time. 60,000 seconds would be, significantly longer. So we HTTPD in the entire 80,000 second runtime, AFL with QEMU is not able to pick up a single crash, whereas FIRM-AFL found 6 unique ones in that time. The bottom line exploit discovery. So they tested this in 2019 against several CVEs that were published in 2018 or earlier that were already known. These were considered one-day CVEs. Not many of them, if any, had proof of concepts written for them. They used AFL to develop proof of concepts because once it crashes, it reports on the input that caused it to be crashed. In most of the cases here, we see anywhere from about a 5 to 10 times speed improvement over execution time. We see very fast AFL crashes. FIRM-AFL is able to crash the program much quicker than its counterpart with using full system mode with QEMU. So, closing remarks. Instrumented fuzzy is heavily dependent upon computation speed. The more test cases you can test a second, the more vulnerabilities you're going to find. The fuzzing programs for foreign architectures with hardware dependencies require a lot of overhead. This is exactly the problem FIRM-AFL, I think, did a very good job of addressing. The optimization of itself, of fuzzing, is still an emerging field. FIRM-AFL did a lot of optimizations to the emulation process of fuzzing, but we're still a great deal away from how a human looks for vulnerabilities and how a fuzzer does. As I stated, fuzzers attempt to get 100% code coverage by testing every possible execution branch, whereas when a human looks for vulnerabilities, we look in the source code, we look at the front end, we make educated guesses, we look at behavior, and we let the behavior guide our testing. Fuzzing attempts to do that, but we just aren't there yet with being able to fully optimize the fuzzing process itself. But we're making great strides in that. FIRM-AFL does a great job of combining the benefits of system emulation and user emulation while excluding many of the drawbacks. Thank you.